What is the nature of vacuum? The worst mismatch in physics is the over 122 orders of magnitude difference between the cosmological constant and the Planck scale vacuum energy density. The mismatch is the so-called cosmological constant problem. A vacuum is the absence of matter, a condition well below normal atmospheric pressure. However, an absolute vacuum is impossible to achieve on Earth. The amount of matter remaining in the system defines the quality of a vacuum. 17th century natural scientist Otto von Guericke invented the vacuum pump. He created a sphere by putting together two copper hemispheres. When he sucked the air out of the copper hemispheres, the resulting vacuum resisted the force of two 15-horse teams pulling in opposite directions, to the amazement of spectators. Vacuum continues to fascinate us today. The latest galaxy survey shows that most energy is contained in the vacuum. On every scale, emptiness dominates. Galaxies are rare floating specks in the vastness of space. And on the smallest scale, tiny atomic nuclei sit in the center of the empty atom. Other data shows that an accelerating expansion dominates the universe future, supplying about 70% of the cosmic energy budget, opening the cosmic web and ripping away and apart galaxy superclusters. My latest manuscript, Can Dimensional Anisotropy Satisfy Mach's Principle, examines how the global cosmic structure formation can lead to dimensional anisotropy. In dimensional anisotropy, the dimensions of space depend on the object's location. The idea satisfies Mach's principle, which shows that local inertia and global mass energy distribution are interdependent. In other words, the motion of distant stars must influence our ability to move, even the maximum speed of our car. Unfortunately, general relativity fails to satisfy this requirement because mass is unaffected by the gravitational field. But what is dimensional anisotropy? Let's consider a square. Seen from the side, it is just a line. If we work against the vacuum in that square, we can pull the square into the third dimension, forming a cube. In the same way, we should be able to stretch the cube into the fourth dimension, creating a hypercube. A fourth-dimensional hypercube represents infinitely greater volume than its three-dimensional counterpart. Therefore, von Geike's experiment showed us the incredible power of vacuum, yet our experience was a contracting vacuum, limited by our three-dimensional world. However, when space expands into the fourth dimension, the volume increases exponentially, accelerating expansion. Emptiness becomes the source of energy, pushing space apart. Cold voids generate expansion, which will dominate the future of our energetic and dynamic cosmos. So what is the origin of dimensional anisotropy? When we isolate a compact wave function from space by an information blocking horizon, we form a field, a topological entity. The separation introduces an energy requirement for their interaction. An interaction satisfies conservation principles and increases spatial curvature differences. As a result, the field topology develops an S shape where positive curvature creates pressure, which compacts space, and negative curvature gives rise to a vacuum, which expands it. Thus, the expanding cosmic structure originates in the microstructure of space. The vacuum energy is a dimensionality function, which is exponentially greater in 4 dimensions. You can read the paper, Can Dimensional Anisotropy Satisfy Mach's Principle, on the Journal of Physics and Astronomy website. In addition, you can learn more information on this work on my YouTube channel and blog, with the appropriate links found in the description below.